Some of the similarities about the rescue simulation and rescue maze is that you use the same navigation algorithms, and you also use computer vision for both of the competitions. You also utilize the same kinds of sensors. So if you do rescue simulation or rescue maze, you would know how to interface with the sensors and get the data from them. Some of the differences that you would encounter with each of the competitions is that rescue maze focus on both the hardware and software aspects of it, while the rescue simulation removes the hardware aspect. So you get to focus more on developing algorithms. Rescue simulation is free, so you can download the simulation software without any cost. And rescue maze, it is costly because you need to purchase the parts for designing the robot. Rescue simulation has a very limited noise from the sensor data, while rescue maze can have a lot more noise because the hardware sensors, it's not perfect. And now Mark is going to talk about rescue simulation.
All right. So the platform that the competition was built off of is called Webots, and it's an environment that allows you to set up for robots, sensors, and different situations. It has a really good physics engine that simulates the real world very well, and there are many robots and different sensors that you can use. So what is Airbus? Airbus is the engine that the competition was running off of, and it was built upon Webots version 2021A. And there are multiple parts to the Airbus engine, as we'll get to later, which is like the supervisor and mapping and controller, etc. So the first main section of Airbus is the supervisor. You can almost think of it as like a control panel. It allows you to spawn in the robot with the software aligned with the robot. It controls the scoring of the robot and the timing and many other things. So the map and robot are the two things that make up the Webots world, and specifically the competition that we did. The map is the environment that the robot will run off of, and Airbus allows for extensive robot customization, where you can control the number of sensors and also the wheels and other things of the robot. And finally, the controller is the software that controls the robot action. It allows for the use of multiple languages and is pretty extensive and very well written, very well, yeah. Finally, our robot, specifically the one that we used for the competition, is made up of 4 main sensors: the LiDAR, GPS, gyro, and camera. The LiDAR measures distance using lasers, and we used it for navigation and mapping. GPS keeps track of the robot's location. We need to send our location to the robot Airbus supervisor when we are doing specific tasks in the competition. And the gyro also measures rotation, which allows for a lot of better navigation. And the camera, we have 3 cameras in total on the robot, 1 on the bottom and 2 on the left and right. The left and right cameras capture the victims that we'll get to later, and the bottom camera captures the tile color. So this is the section that our teammate, that Jeffrey, unfortunately wasn't able to come here. He worked on this, so I'll be giving a brief description of it as best as I can. The map itself is made up of tiles in a X by X order. It splits the board up into more manageable chunks, and it's made up of different colored tiles as well as different tile walls. The tile colors can be like silver, brown, and black, which are representative of other things in the simulation, like a swamp, black hole, checkpoint, etc. And the tile walls are also split into 3 chunks: full tile walls, half tile walls, and curved walls. The search that we did for the maze competition is called breadth first search. And it's considered a greedy algorithm, which basically is look for the most optimal route in the ones that you are currently given in your local scenario situation. And it saves an optimal path to reach the tile once we have completed the entire maze. And it uses a FIFO queue, which is first in, first out. When exiting the maze, once you've searched through the entire surroundings, it relies on the stored map and breadth for search maze to find the starting tile again. And it travels to the starting tile with the most efficient route.
All right, so now that we have navigation down, we use computer vision and image processing to find the victims and the hazards. So for image processing, we use a tool called OpenCV, and it comes with a lot of helpful functions to extract the important information from the camera image. And it's needed to identify the victims and the hazards using the camera. So as you can see here, we have these are our victims. The H, the S, and the U stands for harmed, safe, and unharmed. And then these four are our hazards. So we have flammable gas, poison, corrosive, and organic peroxide. So imaging processing, we have a process to go through until we finally get the final result. So the first step is changing our color space. Then we have image smoothing, and along with that comes image thresholding. Then we find the contours. And last, we have extracting our region of interest. So first step to do is change the color space. So OpenCV stores the images as BGR by default. It's also known as the RGB color space. So it stands for red, green, and blue. And the combination of the red, green, and blue intensities create all the colors. So you can see on the left here, our original image, that's the RGB image. However, we typically convert to a grayscale or HSV, which are other color spaces for thresholding functions, which we'll get to later. So in the middle, we have our grayscale image, and that basically just removes all color from our image, and it includes all gray, all shades of gray. Darkest is black and the brightest is white, and we have all the shades of green in between. And on the far right here, we have our HSV image, and this is used when we mask out color with a function called inRange. Now we use HSV because it's much better at defining color than RGB because it works in different lighting conditions. So HSV stands for hue, saturation, and value. Hue is basically the actual color. Saturation is the intensity of the color, and value is the brightness of it. Next up is image smoothing. So as with all other sensors, you're going to get some noise. And in the case of images, noise can be like some visual artifacts or random pixels that you don't want in the image. So we use blurring and filtering to smooth out our image. So on the left here, we have our original image. And you can see it's not a bad S. But since it's not blurred or filtered out, we get a lot of these sharp edges in the S. So it might not recognize that as a nice smooth line. You can also see that there's some areas of this S that are like, some of it is really black, and then some of it in the curve are kind of lighter shade of gray. So we can blur it to help get it into one uniform color. And then we also have it so that's one smooth line all around. However, blurring does lose some of the detail. It's not as sharp as it was before, so it's not as clear. After that, we have image thresholding. So the step after this is finding contours. And finding contours requires an image that is a pure black and white image. So you can't have any shades of gray. It must be a black and white image. So this is why we need image thresholding. So in this case, we use a binary threshold. And how it works is you check all the pixels of the image and you check that against the threshold value you set it to. If your pixel value is less than threshold, you set it to 0. And if your pixel value is greater than the threshold, then you set it to the max value, which is typically 255 since that's white. So as you can see here, we have our original grayscale image, and on the right, we have our thresholded image. And in this case, our threshold value is 120, which is kind of an in-between gray. So our dark gray turns into black, and our light gray turns into white. Now that we have a thresholded image, we can now find contours on it. And what contours are is basically the white blobs that you see on the black background. So if we go to the previous slide, all this white area here is your contours that you're going to find. So obviously, if you want to find the contour, the object that you want to find needs to be a white. And once you find your contours, you're going to want to do some filtering on it, because sometimes you're going to see a contour that isn't the object that you want. So some common attributes of the contours that we want to filter is the contour area and the aspect ratio. And last, we have extracting the region of interest, or the ROI. So when you get the initial image frame from the camera, you get this big image. Now we want to get the S here, but there is the blue wall here, but we will only want to do the operation on this S. So what we can do is we can get a cropped out portion of image called the region of interest. So what we did here was we masked out the blue background of the walls using cv2.inRange. And then we found contours on that image. And then this is what we get here for our mask. And then we drew a bounding rectangle around the contour. And bounding rectangle is just one of OpenCV's functions for contours. And once we got the bounding rectangle, we simply crop that from the threshold image to get our region of interest. Now comes victim recognition, which is a very important part because we need to rescue our victims from the maze. So here we have our H, S, and U again, and the method that we use to identify them is something called the slicing method. So what we did here was we sliced our region of interest into 3 horizontal sub-images. So we have our top image, our middle slice, and our bottom slice. We found contours for each slice, and then we counted them up for each one. So for H, we have 2 contours on top, 1 contour in the middle, and 2 on the bottom. The S, we have 1 contour on the top, 1 contour in the middle, 1 contour on bottom. In the U, we have 2 on top, 2 in the middle, and 1 on bottom. So now with this, we have an easy way of differentiating the letters from each other. Now with identification, we came across a major issue, which was the misidentifications. So some of the problems we encountered was that it would see an obstacle as a victim. Only part of the letter was visible in the region of interest, so it wouldn't identify it correctly. Sometimes it would miss victims on half walls, and it would also miss victims on shadow walls. So some of the solutions we came up with for these problems was comparing the contour area, and that was for the obstacle problem, checking the aspect ratio so that the entire letter would be in the frame, having a different aspect ratio to be checked for the half walls. And then last, for the shadowed wall problem, all we had to do was just change the threshold value. So when we check the contour area for the obstacle problem, this is basically what our region of interest in our slices will look like when it's on obstacle. So our solution was the slicing method. So we just counted up the contours for each one. So in the case of this one, it sees 1 contour for the top, 1 contour for the middle, and 1 contour on the bottom. So since it sees that, it thinks that's an S, but it's actually an obstacle. So that's why we got a misidentification. So how we solve that, we checked the entire contour area. We saw that it was a much greater value than what the contour area of an S would usually be. So we knew that if the contour area was above a certain threshold, we knew it had to be an obstacle and not an S. Okay, for the half wall problem, we had to modify the aspect ratio check. So if the robot was going forward and it was on a regular wall and there is a victim, it would just see it simply like that. But on a half wall, the robot isn't looking at the victim straight. It will only see it when it's turned at an angle. So it won't be this big. It will see it as a very thin H. So we had to make it check if the robot was turning and have a separate aspect ratio check for a thinner region of interest. Now for hazard identification, the attributes that we checked for was color and also the angle. So color was pretty simple. So first we have our flammable gas and our organic peroxide. Those both have red in them. So immediately we could go and check our region of interest. If any of it has red in it, we know that it could either be a flammable gas or it can be organic peroxide. Then from there, we checked if there's any yellow in it. If there was yellow, we knew it had to be organic peroxide. And if there was no yellow, it was flammable gas. Now for poison and corrosive, those are both black and white. So what we did for that is we checked the bottom half of each one. The poison has a very low amount of black area in the bottom half, while the corrosive has a lot of black in the bottom half. That's basically how we checked for if it was poison or corrosive. However, since poison and corrosive is black and white and the victims, the HSU is also black and white, we had to distinguish them from each other. So that's where the angle, the rotation comes into play. So OpenCV has a function called min area rect, which also returns the angle of rotation of your contour. So we checked for the angle of our contour, and we knew that our hazards, they're rotated at a 45-degree angle. So if it was at a 45-degree angle, that's a hazard. But if it's just at a 90-degree angle, then it's a victim.
All right, so moving on. The last most integral part of the robot competition is the mapping, which allows you to get more bonus points. And again, unfortunately, this is the part that Jeffrey, our missing team member, worked on. So I'll give a brief description of what it does. The mapping is basically a matrix style numerical / character translation of the world itself that you previously have stored. You can see that the walls represent ones, the black wall represents twos, the purple square represents eights, etc. And this, providing an accurate map, given the knowledge you had previously, gives up to a 100% or double bonus score increase. So when facing all of these prior tasks, obviously you're going to face many issues, and to get through these issues and to be able to solve them and make a more sturdy and comprehensive robot, we had to go through many hours of testing. So to begin, the testing process is made up of multiple different parts, which includes identifying the problems, prioritizing the issues, creating the test arenas or worlds in this case, doing singular unit tests, and then finally integrating all of the sections that we tested individually. So for our competition specifically, these are some of the main issues that we came across while completing our robot. Some of these included things like consistent victim detection, navigation with half walls and curves, obstacle detection, traversal and avoidance, and mapping with high accuracy. So when prioritizing the test cases, I want to say that it's not saying that none of these are important. It's just that to complete some of the later issues, you need to have these completed first. For example, to complete mapping, you have to be able to navigate through the entire maze first with accuracy, so you get a high score in mapping. So next, you would create test arenas or test worlds in our case that allow for comprehensive testing of the specific unit that you want to test for. Webots allows for a pretty good tool to create worlds to your desired complexity, which is called the world editor. And as you'll see later, it allows you to create worlds that specifically you can test for curved walls, half walls, victims, etc. So next is unit testing. Unit testing is basically when you test for a specific section of the robot that has a issue that you want to look for or to try to solve. For example, navigation. Navigation we struggled a lot with curved walls and half walls. So we created a world primarily for curved wall testing. You'll see that there are little other extraneous variables. So there would be like no victims here, but just curved walls, and curved walls to the extent so that you can find every single edge case or unpredicted problem that might occur with the navigation in this world. Next, we created a unit test case for victim detection. This world specifically contains hazards or victims on every single wall. You can see there are 2 H's here, placards here and here, S's on the bottom, and many more victims, letters, and placards all around that world. And the navigation here is obviously very simple. So the primary focus here was for victim testing. Lastly, once the unit testing has been comprehensively tested and is both reliable and repeatable, you move on to integration. So one of the first integrated tests that we did was half walls and victim detection, which is when we tested victim detection on specifically half walls. As you can see, this world is huge and is made up of victims solely on half walls, like tight corner half walls here, here, and here, and many other places. As Peter said earlier, we had issues with victim detection on half walls, so this was a perfect world to test on for all of the edge cases that you might encounter. And finally, the last world that we tested on included basically all of these scenarios to try to integrate and incorporate every single portion of the robot to make sure that it was comprehensive enough and ready enough for the competition itself. You can see that this world contains black holes, swamps, checkpoints, silver tiles, obstacles, curves, etc. So, and finally.
Yep. So now we're going to show a video of one of the runs that they had for our the world competition. So you can see on the top, we have our score, how much time is left, and then it has a message log of what's going on. So you can see we got a successful hazard type and identification points.
Peter, I'm sorry to interrupt you. I think the score and the stuff at the top is currently being blocked. I think it's blocked by something on your end. I'm not sure.
Probably the Zoom thing.
Yeah, if you move that out of the way, there you go. Now we can see it.
Okay.
Thank you.
Yeah.
So as you can see, the robot didn't try to get through that half wall earlier when going through that dead end. That's a very good point by the navigation section on Jeffrey's end.
Detected a hazard.
Mm.
It also checked on the tile for the black hole, and it knew not to go straight and fall into the black hole. It does it again.
And if any of you previously forgot, that's due to the fact that there's a color sensor on the bottom, and you can see that there's a little lip right before the black hole. So when we see a black color on the ground, just make sure to not enter that area.
Did you guys happen to show the robot configurator, how you built the robot and chose the sensors and the position?
Oh, that was earlier when we were talking
that
about
was in an earlier slide.
Yeah.
Oh, okay, I missed it. Sorry.
Yeah, it was briefly discussed, but there was a certain budget to the robot, and we could only choose so many sensors because sensor costs a certain amount of money, and we couldn't go above that total budget cost.
Okay, so now the robot has searched through the whole maze, so now it's making its way back to the starting tile.
And as you can see, the robot's making the most accurate and the fastest route back.
I'm just gonna pause it right there. Yeah, so we can see the final score is 1,233. You can see at the top here, we have our map correctness and map bonus. So we can see that the mapping, it does provide a significant bonus points for us. And we spent a total of 4 minutes and 47 seconds in this map. And this was round 8. This was one of the harder maps to do. So the fact that we were able to do in 4 minutes, 47 seconds out of the 8 total minutes was pretty significant. All right, thank you everyone for listening. And now we would like to open up for some Q&A. So if anyone has any questions, feel free to ask them.
No, I will stay here for about like 5 minutes, but in the meantime, same as usual, please look at the chat. And I put out a link for the next workshop. It's run by MathWorks, and if any engineers, MathWorks, the name of MathWorks should be extremely familiar to you guys. And they're gonna hold a free workshop on how to use their fancy or fascinating the environment to use it with the Lego Mindstorms. So it should be very interesting. And also there's a link to get the free license to the MATLAB. So it's all in the chat. So then please go ahead to click on that link and so you can join the workshop. Thank you so much for your presentation, Mark and Peter. That was very good. Very informative.
Thank you for having us.
You're welcome.
Thank you. Great job.
Thank you so much.
Thank you for listening.